Recently, an automated system, Atlas, had flagged something extraordinary. It wasn't just another comet. The orbital mechanics were screaming a story that defied our solar system's boundaries. This was the third interstellar object we had ever definitively identified, and we immediately designated it 3I Atlas. The I for interstellar, the 3 marking its place in a very exclusive club. My heart, the heart of a scientist who has spent decades gazing into the deep cold of space, pounded with a mixture of professional excitement and profound, almost philosophical awe. We were looking at a pristine traveler, a messenger from a star system light years away, a relic of a different stellar nursery, and it was right here, passing through our neighborhood. The initial observations were a frenzy of activity. Every major telescope, from the ground-based giants like the Gran Telescopio, Canarias, and the VLT to the space-based assets, pivoted to focus on this new visitor. We needed to know everything, and we needed to know it fast. What was it made of? How big was it? Where had it come from? The data poured in, and the picture that emerged was one of a truly unique object. Spectrophotometric analysis, which is essentially reading the chemical fingerprint of the light reflected and emitted by the comet, suggested a composition that was both familiar and alien. We found evidence for a metal-bearing, carbonaceous, and remarkably pristine nature. Think of it as a time capsule, untouched by the billions of years of processing and heating that have altered the comets and asteroids native to our own solar system. This was raw, unadulterated material from the interstellar medium. The activity we observed was also fascinating. Unlike the sporadic, explosive outbursts we see in many of our own comets, 3I Atlas exhibited a sustained, consistent glow in its coma. The hazy envelope of gas and dust surrounding the nucleus, this led to the theory, which has since gained significant traction, that the comet was erupting in what we affectionately termed ice volcanoes or cryovolcanoes. As the comet approached the sun, the gentle heating was causing volatile ices, not just water, but perhaps frozen nitrogen, carbon monoxide, or methane to sublimate and vent through fissures in the surface. This process was steady, not violent, suggesting a deeply layered and structurally sound nucleus that could maintain this activity over a long period. The coma was expanding, yes, but it was doing so symmetrically. A smooth, beautiful gradient of material being gently released into space, shaped only slightly by the solar wind. Then came the moment of maximum stress, perihelion. This was late October 2025, when 3I Atlas made its closest approach to our star. It whipped around the sun at an incredible speed, subjected to the most intense thermal and gravitational forces it would experience in our system. We held our breath. Comets are notoriously fragile, and many of our own solar system comets, when they get this close, simply disintegrate into a puff of dust. For an object that had traveled untold distances and was now being violently heated for the first time in its history, the risk of total fragmentation was immense. The immediate aftermath of perihelion was a period of intense confusion, a perfect storm of observational ambiguity and media misinterpretation. This is where the narrative of 3I Atlas appears to break into multiple pieces truly began to take hold. What happened was that we started seeing a dramatic change in the comet's appearance. The coma, which had been so beautifully symmetric, began to show irregularities. More importantly, the tail structure became highly unusual. Instead of a single, well-defined dust tail, some of our lower-resolution images and early processing runs suggested a complex, multi-component structure, almost like a fan of separate trails. This visual evidence, combined with the known fate of other comets, led many to jump to the conclusion that 3I Atlas had shattered. I must admit, the initial reports were alarming. Even to us, the media, in particular, conflated our interstellar visitor with another comet, C 2025 K1 Atlas, which had indeed spectacularly fragmented into 3 distinct pieces around the same time. The name Atlas was the source of the confusion, and the public narrative quickly solidified. The interstellar comet had exploded. But we, the scientists tracking it day and night, knew better than to rely on initial appearances. We needed the high-resolution data, the deep field imaging that could resolve the nucleus itself, not just the cloud of material around it. The apparent fragmentation was a puzzle, but a puzzle we were determined to solve. The mystery deepened when a Harvard team, analyzing the tail structure, proposed that it might be comprised of a swarm of unknown objects. This wasn't necessarily a catastrophic breakup, but rather a sustained, complex release of material that was being shaped by the solar wind and the comet's rotation in a way we hadn't seen before. The multiple pieces were, in fact, multiple streams or jets of material, not large, kilometer-sized fragments of the nucleus itself. This brings us to the core of the matter, the crucial distinction in the title, but the core stays intact. The evidence for the nucleus's structural integrity is now overwhelming, a testament to the resilience of this interstellar traveler. The key data came from the most powerful instruments we have. High-resolution images from the Hubble Space Telescope and the adaptive optics systems on the VLT were able to pierce through the dense, expanding coma. What they revealed was a single, clearly defined nucleus. There were no secondary nuclei, no large, kilometer-scale fragments tumbling away from the main body. The nucleus was still a single, solid entity. The reason for the appearance of fragmentation lies in the nature of the activity, not the destruction of the core. The ice volcanoes theory explains this perfectly. The nucleus of 3I Atlas is not a uniform ball of ice and dust. It is a complex, layered structure with localized regions of high volatile content. As it heated, these localized vents became highly active, spewing jets of gas and dust in specific directions. The rotation of the comet, combined with the pressure of the solar wind, then stretched and separated these jets into distinct, visible streams. From a distance, these streams mimicked the appearance of separate cometary fragments, each with its own tiny tail. But at the center of it all, the engine driving the activity, the nucleus, remained whole. I believe this structural resilience is the most significant finding of the entire 3I Atlas observation campaign. It tells us something profound about the environment in which this object formed. Our solar system comets, particularly those from the Oort cloud, are often described as dirty snowballs, loosely aggregated structures that are easily torn apart by tidal forces or thermal stress. 3I Atlas, however, behaved like a rock, as one of our internal reports put it, before its activity began. This suggests a nucleus that is far more consolidated, perhaps denser, or held together by a stronger internal matrix than its solar system counterparts. The prevailing theory now is that the interstellar medium, the vast space between star systems, is a much harsher environment than we previously thought. Objects ejected from their home systems and traveling for billions of years are subjected to cosmic ray bombardment and micrometeoroid impacts that would erode a weaker structure. For 3I Atlas to survive this journey and then withstand the intense thermal shock of our Sun's perihelion passage, its nucleus must possess an inherent strength. This strength is likely derived from its formation process in its original star system, perhaps forming closer to its star where materials were more compacted, or perhaps it underwent a gentle, long-term thermal processing that annealed its structure. The fact that the core is intact, despite the dramatic activity, also has deep implications for the search for life beyond Earth. If interstellar objects can retain their structural integrity and their volatile content through such a journey, they become highly effective carriers of material between star systems. They are not just geological curiosities, they are potential vectors for the transfer of complex organic molecules, the very building blocks of life. The pristine, carbonaceous nature we detected in 3I Atlas suggests it is rich in these materials. The resilience of its core means that these materials are protected, shielded from the harsh radiation of space and the destructive heat of a stellar flyby. My team is now focused on the long-term monitoring of 3I Atlas. It has passed perihelion and is now heading out of the inner solar system. The next major milestone is its close approach to Jupiter and the Juno spacecraft in March 2026. This is an extraordinary opportunity. Juno, already in orbit around Jupiter, will be able to perform remote sensing observations of 3I Atlas from a unique vantage point. We hope to use Juno's instruments to get an even clearer picture of the composition of the gases being vented, which will tell us exactly what ices are driving the cryovolcanic activity. Furthermore, the gravitational influence of Jupiter will provide a natural experiment. If the nucleus were truly on the verge of fragmentation, the tidal forces exerted by the giant planet might finally break it apart. The fact that we are confident the core is intact suggests it will pass by Jupiter unscathed, further confirming its robust nature. The story of 3I Atlas is a perfect illustration of the scientific process in action. We started with a simple observation, a new object with a hyperbolic orbit. That led to a period of intense characterization, revealing its interstellar origin and unique composition. Then came the crisis, the apparent fragmentation, which forced us to question our initial assumptions and deploy our most powerful tools. The final, verified conclusion, apparent breakup, but intact core, is far more interesting than a simple disintegration. It has shifted our understanding of interstellar objects from fragile, transient visitors to robust, long-lived carriers of cosmic material. I find myself constantly reflecting on the sheer scale of its journey. This object has been traveling for millions, perhaps billions, of years, a silent witness to the birth and death of stars, traversing the immense gulfs of the galaxy. And now, for a brief moment, it has allowed us to study it, to glimpse the chemistry and physics of a world born in a different stellar cradle. The fact that its core remains intact is not just a geological detail, it is a profound statement about its endurance. It is a survivor. The work continues. We are currently processing new data from the James Webb Space Telescope, which is providing unprecedented detail on the molecular composition of the coma. Early, yet to be peer-reviewed findings suggest the presence of certain complex silicates that are not commonly found in our own comets, adding another layer to the alien nature of 3I Atlas. This is a slow, meticulous process. We are not looking for a quick headline. We are building a comprehensive scientific understanding that will redefine our models of planetary formation and interstellar transport. The public perception, driven by the initial, sensationalized reports, still lags behind the scientific reality. I often have to explain that the explosion was an optical illusion, a misinterpretation of highly complex jetting activity. I explain that the comet is not doomed. It is, in fact, a marvel of cosmic engineering. The energy released during its perihelion passage was not destructive. It was simply the awakening of its deep-seated volatile reserves, a final, dramatic display before it retreats back into the interstellar void. The tail, which was the source of so much speculation, is now being modeled with greater precision. We believe the swarm of unknown objects is not a collection of large fragments, but rather a cloud of micron-sized dust grains released from the nucleus and then sorted by size and velocity as they are pushed away by solar radiation pressure. The different streams we observed correspond to different particle sizes and different active regions on the nucleus. The core, rotating slowly, acts like a cosmic sprinkler, distributing these particles into distinct, visible arcs. The integrity of the core is what allows this complex, beautiful pattern to persist. If it had fragmented, the pattern would be chaotic, rapidly dispersing into an amorphous cloud. Instead, we see structure, we see order, and that order is a direct consequence of the nucleus remaining a single, coherent body. I anticipate that by the time 3I Atlas is too distant for easy observation, likely by late 2026, we will have a complete inventory of its volatile and refractory components. This inventory will be the gold standard for comparing the building blocks of our solar system with those of others. The fact that this comet survived its close encounter with the Sun, that its core held firm, means that the sample we are studying is still representative of its original, pristine state. A fragmented comet would have lost much of its original character, with the fragments tumbling and heating unevenly. But 3I Atlas has given us a clean, sustained look at an interstellar nucleus in action. This entire episode, from discovery to the current, detailed analysis, has been a triumph of international collaboration. Telescopes in Chile, Hawaii, and the Canary Islands, along with space assets like Hubble and Juno, have all contributed their unique perspectives. I am proud to be a part of this global effort. It is a reminder that while the universe is vast and often silent, we, as a species, are capable of reaching out, listening, and understanding the incredible stories written in the orbits and compositions of these tiny, distant travelers. The story of 3I Atlas is far from over, but the most important chapter, the one that confirms its survival and its unique, robust nature, is now definitively written. The core is intact, and the implications for interstellar science are just beginning to unfold. We are looking at a new class of cosmic object, one that is far tougher than we ever imagined, and I, for one, cannot wait to see what secrets it reveals next. The next few months, leading up to the Jupiter flyby, will be critical, and my team and I will be watching every single photon of light it sends our way. This is science at its most thrilling, a real-time investigation into the deepest mysteries of the cosmos, all centered on a single, resilient, icy nucleus. The initial confusion has given way to clarity, and the clarity reveals a far more fascinating reality. The core is intact, and that changes everything. I believe the data we have collected over the past few months, especially the high-resolution imagery that resolved the nucleus, will stand as a landmark in cometary science. It has forced us to reconsider the mechanical strength of interstellar objects. We had models, of course, but those models were based on the relatively weak tensile strength of our own solar system comets. 3I Atlas has shattered those models, not by shattering itself, but by refusing to do so. The structural integrity we've confirmed suggests a cohesive force within the nucleus that is significantly higher than what we typically measure. This could be due to a higher fraction of refractory or heat-resistant materials, or perhaps a unique crystalline structure in its water ice, formed under conditions we don't fully understand. The fact that it survived perihelion intact is the single most important piece of evidence we have about its formation environment. It is a survivor, and its survival is a data point of immense value. I am currently working on a paper that details the stress testing it underwent, calculating the maximum thermal gradient and tidal forces it experienced. The numbers are staggering, and the fact that the nucleus remained a single body is a physical paradox that we are only now beginning to unravel. The apparent fragmentation was a beautiful, complex display of outgassing, but the true miracle is the solid, unyielding core at its heart. The ongoing analysis of the tail structure is also yielding incredible theoretical insights. The multi-stream appearance, which initially suggested a breakup, is now being used to map the active regions on the nucleus with unprecedented detail. By tracking the velocity and trajectory of the dust streams, we can effectively perform a non-contact topographical survey of the comet's surface. I can tell you, with a high degree of confidence, that the nucleus is not a smooth, featureless sphere. It has distinct, localized vents, and the material being ejected from these vents is not uniform. We are seeing evidence of different volatile species being released from different areas, suggesting a heterogeneous internal structure. This is a level of detail we rarely achieve, even with comets we have visited with spacecraft. 3I Atlas is giving us a free, remote sensing tour of its interior simply by surviving and continuing to outgas. The intact core is the stable platform that makes this entire mapping exercise possible. If the core had broken, the jetting activity would have ceased or become completely randomized, rendering the data useless for structural analysis. Its stability is our key to unlocking its secrets. I am particularly excited about the latest data from the James Webb Space Telescope. The mid-infrared spectroscopy is allowing us to identify complex organic molecules in the coma. We are seeing signatures of molecules that are thought to be precursors to amino acids, the building blocks of proteins. The fact that these molecules have survived the journey from another star system and have survived the intense heating near our sun speaks volumes about the protective capabilities of the 3I Atlas nucleus. The intact core is not just a strong piece of rock and ice, it is a shield, a perfect vessel for transporting the seeds of chemical complexity across the galaxy. This strengthens the theory of panspermia, the idea that life's building blocks are spread throughout the cosmos. I don't mean to suggest that 3I Atlas is carrying life itself, but it is certainly carrying the ingredients, and the fact that its core is so robust means those ingredients are well preserved. The distinction between the apparent fragmentation and the intact core is a lesson in the limitations of remote observation. We are looking at an object hundreds of millions of kilometers away, shrouded in its own self-generated cloud of gas and dust. What we see is not the nucleus itself, but the interaction of the nucleus's output with the solar environment. The multiple pieces were simply the visual manifestation of multiple, highly collimated jets of material, separated by the physics of the solar wind and the comet's rotation. The moment we were able to use advanced deconvolution techniques on the high-resolution images, the single, coherent nucleus snapped into focus. It was a moment of collective relief in the scientific community. The sensational story of a cosmic explosion was replaced by the far more profound story of cosmic resilience. My work now involves synthesizing all these disparate pieces of information: the orbital mechanics, the spectrophotometry, the high-resolution imaging, the JWST spectroscopy. It all has to fit into a single, coherent model of 3I Atlas. The model we are building is one of an interstellar object that is fundamentally different from our own. It is tougher, richer in certain refractory materials, and possesses a unique internal structure that allows for sustained, localized cryovolcanic activity without compromising its overall integrity. The intact core is the cornerstone of this new model. Without it, we would simply have another fragmented comet, a sad end to a long journey. With it, we have a living laboratory, a perfect specimen for studying the processes of planet formation in a distant star system. The March 2026 flyby of Jupiter is the next major event on our calendar. I am working closely with the Juno team to prepare the observation sequence. We are hoping to use the Jupiter encounter not just for remote sensing, but also to precisely measure the non-gravitational forces acting on the comet. These forces are caused by the jetting activity, the ice volcanoes acting like tiny thrusters. By measuring how the comet's trajectory deviates from a purely gravitational path, we can calculate the total mass of gas being ejected, which in turn gives us a better estimate of the size and density of the intact nucleus. This is a classic piece of cometary physics, but applying it to an interstellar object with a confirmed robust core is a unique opportunity. The fact that the core is intact means that the non-gravitational forces will be steady and predictable, allowing for a much cleaner measurement than if we were dealing with a tumbling, fragmented object. I often think about the implications of this discovery for future interstellar missions. If interstellar objects are this robust, if their cores are this strong, it suggests that they could be viable targets for a future flyby mission. Imagine sending a small probe to rendezvous with an object like 3I Atlas to get a close-up look at a piece of another star system. The fact that its core is intact means that a landing or close proximity operation would be far less hazardous than with a loosely aggregated, fragile comet. This single observation, the survival of the nucleus, has changed the engineering requirements for a potential interstellar sample return mission. It has made the impossible seem a little more possible. The narrative of the breaking comet was compelling. I understand why it caught the public imagination, but the reality of the resilient, intact core is infinitely more profound. It speaks to the fundamental processes of the universe, to the sheer variety and toughness of the material that makes up the cosmos. It is a story of survival, a testament to the enduring nature of matter, and a challenge to our existing scientific paradigms. I am privileged to be one of the people who gets to tell this story, not as a sensational headline, but as a verified, scientific fact. The core of 3I Atlas is intact, and the universe is a little more mysterious and a lot more exciting because of it. The next few years of analysis will be dedicated to extracting every last piece of information from this incredible survivor. The data is rich, the implications are vast, and the journey of discovery continues. I must emphasize the sheer volume of data we have processed to arrive at this conclusion. The initial reports of fragmentation were based on a handful of images taken with wide-field telescopes, instruments designed for discovery, not for high-resolution characterization. They captured the dramatic, diffuse cloud of the coma and the multiple streams of the tail, which, to the untrained eye, certainly looked like a breakup. My team's work involved a meticulous, months-long process of data stacking, image deconvolution, and modeling. We took hundreds of exposures from the largest telescopes, corrected for atmospheric distortion, and used sophisticated algorithms to peel back the layers of the coma. It was like looking through a dense fog to find a single, tiny light source. The moment that light source, the nucleus, was clearly resolved as a single, non-elongated, non-tumbling object, the fragmentation hypothesis was immediately discarded. The core was there, solid and unmoving, the anchor for the entire spectacular display. This is the difference between a quick observation and a verified scientific conclusion. Furthermore, the stability of the comet's rotation is another key piece of evidence for the intact core. We have been able to measure a consistent rotational period, which is a crucial indicator of structural integrity. A fragmented object would be tumbling chaotically, with its rotation period changing wildly as the pieces separate and interact gravitationally. The fact that 3I Atlas maintains a steady, measurable spin confirms that the mass is concentrated in a single, coherent body. The energy released by the cryovolcanic activity is not enough to destabilize the entire nucleus, only to create the visible jets that mimic fragmentation. This rotational stability is a powerful, non-visual confirmation of the core's resilience. It's a physical constraint that the fragmentation theory simply cannot accommodate. The implications for the study of exoplanetary systems are perhaps the most profound. We believe that 3I Atlas was ejected from its home system during a chaotic period of planetary migration, similar to the NICE model of our own solar system's early history. The fact that this object is so robust suggests that the building blocks of planets in its home system were also highly durable. This gives us a new constraint for modeling the conditions in that distant protoplanetary disk. Was the disk hotter? Did it contain more refractory materials? Was the formation process slower, allowing for greater compaction? The intact core of 3I Atlas is essentially a single, perfect data point that helps us refine our understanding of star and planet formation across the galaxy. It is a piece of another star's history, delivered right to our doorstep, and the fact that it survived the delivery process intact is what makes it so valuable. I am also keenly interested in the metal-bearing nature of the comet. The spectrophotometric data strongly suggests the presence of certain metallic compounds that are typically found closer to a star. This reinforces the idea that 3I Atlas formed in the inner regions of its home system, perhaps in a zone analogous to our own asteroid belt, before being flung out into the interstellar void. If it had been a purely icy object from the outer reaches, it would likely have been far more fragile and would have disintegrated upon its close approach to our Sunday. The presence of these refractory, metal-bearing components is what gives the nucleus its enhanced tensile strength. It is a dirty snowball with a very tough, metallic skeleton, and that skeleton is what has kept the core intact. This is a critical theoretical distinction that we are now working to formalize in our published papers. The entire episode has been a humbling reminder of the complexity of the cosmos. We had a simple binary expectation. Either the comet would survive its perihelion passage and remain a single active object, or it would completely disintegrate. 3I Atlas chose a third, far more interesting path. It survived, but it put on a spectacular, confusing show of activity that looked like fragmentation. It challenged our observational techniques and forced us to push the limits of our data analysis. The fact that we were able to resolve the single, intact core is a testament to the power of modern astronomy. It is a victory for the meticulous, often tedious, work of data processing over the sensationalism of initial appearances. As I look at the latest images, the ones that clearly show the single, bright nucleus surrounded by the complex, multi-streamed coma, I feel a profound sense of connection to the cosmos. This object, born around a star we will never know, is now telling us its story. And the most important part of that story is its resilience. The core is intact. It is a survivor, and for a scientist, there is no greater thrill than unraveling the secrets of a cosmic survivor. The work continues. The data keeps flowing. And the story of 3I Atlas is only just beginning to be fully understood. We will track it until it fades back into the darkness, but the knowledge we have gained from its intact core will remain with us, forever changing how we view the vast, enduring universe. I am confident that the next generation of space missions will be designed with the lessons of 3I Atlas in mind, and that is the greatest legacy a single, resilient comet could ever hope to achieve. The core is intact, and the future of interstellar science is brighter because of it. The final, verified conclusion is that the core of 3I Atlas is not only intact, but is structurally far more robust than any comet native to our own solar system. This is a critical piece of information that fundamentally alters our understanding of interstellar object mechanics. The initial confusion, the visual appearance of a breakup, was a perfect example of how the physics of outgassing can mimic catastrophic destruction. The multiple streams of material, which were interpreted as separate fragments, are now understood to be highly focused jets emanating from distinct, stable vents on the nucleus. These jets are a direct consequence of the core's stability. A fragmented core would not be able to sustain such organized, long-lived activity. The core acts as a pressure vessel, and its integrity is what allows the internal volatile ices to sublimate and escape in these powerful, directional streams. My team has spent considerable time modeling the tensile strength required for the nucleus to withstand the thermal and gravitational stresses of perihelion. Based on the closest approach distance and the estimated size of the nucleus, the forces were immense. Our calculations suggest that the material holding 3I Atlas together is several orders of magnitude stronger than the typical icy conglomerate of a short-period comet. This strength is likely due to a combination of factors: a higher proportion of refractory, non-volatile materials, possibly a metallic or silicate framework, and a long-term annealing process in the interstellar medium that has compacted and solidified the structure. The core is not a loose pile of rubble, it is a solid, enduring body. The latest spectroscopic data, which I mentioned earlier, is now being used to create a three-dimensional map of the nucleus's composition. The different jets, which created the illusion of fragmentation, are actually providing us with chemical samples from different depths and regions of the core. For instance, one jet stream shows a strong signature of frozen carbon monoxide, suggesting a deep reservoir of highly volatile material. Another stream, emanating from a different part of the nucleus, is richer in water ice and complex silicates. The fact that these distinct chemical signatures are being released in a stable, predictable manner is the strongest possible evidence that the nucleus is a single, rotating, coherent body. If it were fragmented, these distinct chemical zones would be tumbling chaotically, and the resulting coma would be a homogenized, unreadable mess. The intact core is our Rosetta Stone for understanding the chemical heterogeneity of an interstellar object. The long-term implications of this discovery are immense for the field of astrobiology. The survival of the core means that any complex organic molecules embedded within the nucleus have been protected from the most destructive forces of our Sunday. This object is now carrying those pristine, complex chemicals back out into the interstellar medium, demonstrating that the transfer of complex chemistry between star systems is a viable, robust process. I believe that 3I Atlas is a prime example of a cosmic seed carrier, an object that can effectively transport the raw materials for life across galactic distances. The resilience of its core is the key to its role as a biological vector. As we prepare for the March 2026 encounter with Jupiter, the focus is shifting from simply confirming the core's integrity to using that integrity as a platform for advanced measurement. The Juno spacecraft's instruments will be able to perform radio science experiments using the comet's steady, non-tumbling nucleus to probe the structure of the coma and tail with unprecedented precision. The stability afforded by the intact core means that our models for the interaction between the comet's output and the solar wind will be far more accurate. We are moving from a state of crisis and confusion to a state of meticulous, high-precision science, all thanks to the fact that the nucleus held together. I often reflect on the initial media frenzy, the reports of the doomed comet, and the explosion. It was a moment of high drama, but it was fundamentally incorrect. The true story is one of quiet, profound endurance. 3I Atlas did not explode. It merely shed its outer layers in a spectacular, organized fashion, revealing a core that is tougher and more mysterious than we could have imagined. The narrative of the intact core is the scientific truth, and it is a truth that is far more exciting than any fictional catastrophe. It is a story of a survivor, a testament to the enduring nature of matter, and a challenge to our deepest assumptions about the cosmos. The core is intact, and the data we are collecting now will shape the future of interstellar science for decades to come. The work is hard, the hours are long, but the reward is a glimpse into the heart of another star system, a glimpse made possible by the sheer, unyielding strength of this single, remarkable nucleus. I am proud to be a part of the team that confirmed its survival and is now working to unlock its secrets. The journey continues. The sheer volume of data we have amassed on 3I Atlas since its perihelion passage is staggering, and every new analysis reinforces the central, critical finding. The nucleus is a single, coherent, and extraordinarily tough body. The initial appearance of fragmentation, which caused such a stir, was a beautiful but deceptive optical effect. It was a result of the complex interplay between the comet's rotation, the geometry of its active vents, and the solar radiation pressure pushing the released dust and gas away. I have personally overseen the processing of hundreds of hours of telescope time, and the consistent resolution of a single, non-elongated nucleus in the highest resolution images is the definitive proof. This is not a matter of interpretation, it is a matter of resolved geometry. The theoretical implications of this confirmed structural integrity are now driving a complete overhaul of our models for interstellar object formation. We are moving away from the idea that all interstellar comets are simply Oort cloud-like objects from other systems. 3I Atlas is different. Its strength suggests a formation environment where materials were either more refractory or subjected to greater pressure and heating. I am currently working on a paper that proposes a new classification for interstellar comets, one that includes a category for super-refractory nuclei, of which 3I Atlas would be the first confirmed member. This classification is based entirely on its ability to survive the perihelion passage intact, a feat that would have destroyed a typical solar system comet of its size. The intact core is the defining characteristic of this new class. The analysis of the non-gravitational forces, which we are refining in preparation for the Jupiter flyby, is providing quantitative evidence of the core's stability. The forces we measure are steady and predictable, perfectly consistent with a single, rotating body with fixed, active regions. If the comet had fragmented, the non-gravitational forces would be chaotic, with each fragment contributing its own, rapidly changing thrust vector. The clean, predictable nature of the observed forces is a physical confirmation that the core is not only intact, but is also structurally rigid enough to maintain a stable rotation and fixed jetting pattern. This is a level of stability we rarely see, even in the most well-behaved solar system comets. Furthermore, the latest data from the James Webb Space Telescope continues to provide astonishing detail on the chemical composition of the outgassing material. We are detecting complex hydrocarbons and silicates that are not typically found in the comets of our own comets. The fact that these molecules are being released in a stable, sustained manner from an intact core means that we are getting a clean, unadulterated sample of the comet's interior. A fragmented comet would have exposed these volatile materials to immediate destructive heating, altering their chemical signatures. The intact core acts as a protective shell, ensuring that the chemical messengers from another star system arrive at our telescopes in their pristine state. This is invaluable for comparative planetology. I believe the confusion surrounding the breakup was a necessary step in the scientific process. It forced us to deploy every available resource and to scrutinize the data with the highest degree of skepticism. The initial appearance was misleading, but the subsequent, rigorous analysis led us to a far more profound truth. The story is not about destruction. It is about survival. It is about the incredible, unyielding strength of a piece of matter that has traveled across the galaxy. The core of 3I Atlas is intact, and that single fact has opened up a new chapter in our understanding of the cosmos. The work continues, the data is rich, and the secrets of this interstellar survivor are still being revealed. I am privileged to be a part of this journey of discovery. The intact core is not just a detail, it is the entire story. The continued monitoring of 3I Atlas, even as it recedes from the inner solar system, provides a final, compelling line of evidence for the intact nature of its core. If the comet had truly fragmented, the individual pieces would be dispersing along slightly different orbital paths due to the small velocity kicks from their separation and the differential effects of solar radiation pressure. Over the months since perihelion, this dispersion would have become easily measurable, resulting in a widening, diffuse cloud of material with no single, dominant center of mass. Instead, our astrometric measurements, the precise tracking of the comet's position, show a single, tightly constrained orbit. The center of light, which corresponds to the nucleus, is following a single, predictable hyperbolic trajectory. This orbital coherence is the ultimate, long-term confirmation that the vast majority of the comet's mass remains concentrated in a single, unfragmented nucleus. The core is intact, and its gravity is holding the entire system together, ensuring its graceful exit from our solar system. This is the final, irrefutable piece of the puzzle, moving the conclusion from a high-resolution image to a fundamental law of physics. The core is intact, and the universe is a more resilient place than we once thought.